Section 3.3. Welcome to the notes. This is a hugely important section. This is really a foundational section in the entire year. I cannot emphasize enough how crucial it is that you understand and are able to apply the two rules that we are going to learn today in section 3.3. It's going to be ubiquitous. There's hardly a single lesson in the entire year when we are not going to be using what we learned today. So not mastering what we learned today is gonna hit you in every single quiz, every single test, every project, everything we do. If you aren't exceptionally good at what we learned today, it's just gonna hurt you every time. So make sure that you master this perfectly. So what we'll do today is we'll learn two additional rules of differentiation. We'll learn a few more of these rules that we need to know by heart, and then we'll talk about what the second derivative is, or third derivative. If you remember from the exercises, there was a question that was find the derivative of f of x equals x times x squared plus 1. And we could do that because we could distribute first, and then we could use the power rule. Today we're going to see how we could have taken the derivative using the fact that it's a product. It's x times x squared plus 1. And you can also do that, but it follows a special rule. If f is the product of two other functions, like u and v, then f prime is u prime v plus uv prime. This has to flow out of your mouth, u prime v plus uv prime. That's the derivative when you have a product, and it is called the product rule. There's a proof in the textbook if you are interested on page 140. You can also write it like that. The derivative of u times v is the derivative of u times v plus u times the derivative of v. So here's a first example. F of x equals 2x plus 1 times x cubed minus x. We could have done that using distribution first and then using the power rule. Yes, we could have, but let's use the new rule that we've just learned. U is going to be 2x plus 1. So this is going to be u, and then this is going to be v. If u is 2x plus 1, then u prime is 2. That's the derivative of 2x plus 1. And if v is x cubed minus x, then v prime is 3x squared minus 1. And now we can just plug in u, v, u prime, v prime wherever they belong. F prime is u prime v plus u v prime. We could stop here, or if we wanted, we could now distribute and reach the cubic polynomial. So that was fine. We could have done it in section 3.2. Here's an example that we could not have done before knowing the product rule. F of x equals x times e to the x. So we're going to choose x equals u, and then e to the x equals v. So u equals x, v equals e to the x. The derivative of that is 1. The derivative of e to the x is e to the x. Therefore, f prime equals u times v, u prime v plus u v prime. If we want to factorize e to the x, this is what we get. It's not necessary to factorize here, because here that's a perfect answer. But when we do more evolved exercises where we need to use the derivative further, factorizing e to the x is often very useful. There's a similar rule for fractions. If a function f is u over v, then the quotient rule looks like this: u prime v minus uv prime over v squared. Make sure when you learn the product rule to also start with u prime v. You always want to start with u prime v. For the product rule, it doesn't seem to matter. For the quotient rule, if you switch these, then it's going to matter a lot. You're not going to get the right answer. So always start with u prime v minus uv prime over v squared. Here's an example of a function y equals 3x over x squared plus 1. So u is going to be 3x, v is going to be x squared plus 1. If u equals 3x, u prime equals 3. If v equals x squared plus 1, v prime equals 2x. From here, it's all just a matter of plugging things in. Y prime equals u prime v minus u v prime over v squared. One note that you may, there's no reason why you would guess that, but just from experience, I can tell you never expand the denominator. When never means 99.9% of the time, it is not helpful to expand the denominator. In fact, it's quite often harmful to expand the denominator. If you have any hope of things canceling up between the top and bottom, it's going to be before expanding the denominator. So do not do not expand the denominator, just leave it as a square. All right, so here's the answer after we've simplified a little bit. So let's put a few things together now that we've studied in the last week. Find the equation of the tangent line to f of x equals x minus 4 over 2x plus 6 at x equals negative 2. The question asks us to find the equation of a line. So to find a line, you know it, we need a point and we need the slope. We need a point and the slope. Let's start with the point first. It's the easier part. We know x equals negative 2, so we need to find y. And to find y, we're going to just plug in x here. So here's for the point x equals negative 2, therefore y equals this, equals that, equals negative 3. So the point where we are looking for the tangent line is the point negative 2, 3, right there. The slope is the derivative. So we will start by looking for the derivative of f of x using the quotient rule. U equals x minus 4 and v equals 2x plus 6. U equals x minus 4, that's a line that has slope 1. V equals 2x plus 6 is a line that has slope 2. So u prime equals 1, v prime equals 2. You're probably going to want to pause the video, obviously, to copy all that, but u prime v minus u v prime over v squared is written like that, and things cancel out very nicely, and we get f prime of x equals 14 over 2x plus 6 squared. So what is the slope of the tangent line? What is the slope at x equals negative 2? We plug in negative 2 here, and we get f prime of 2 equals 7/2. And that's it. We just need to write the answer now. The tangent line is y minus 3 equals 7 over 2 times x plus 2. Just a little rough sketch of the situation. Again, we do not need that to solve the problem, but it's interesting in the end to see what all of this looked like. It's a rational function, and then you have a line that just touches here at x equals negative 2, y equals 3. Determine the derivative of y equal tan x. That's interesting. It seems to fall out of nowhere, but the reason why it's in this section is that, of course, tan x is sine x over cosine x. So that's a great application of the quotient rule, because we don't have to memorize tan x if you want. We can just figure it out using what we know about sine x and cosine x. So u equals sine x, v equals cosine x, and the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Plugging everything in, we get u prime v minus u v prime over v squared. Now that's interesting, because we get cosine squared x plus sine squared x over cosine squared x. We can simplify that, clearly, but there's actually two ways of simplifying. One is to be like, hey, this is equal to 1. I know that, it's Pythagoras. And if you do that, then the derivative becomes 1 over cosine squared, which is written here. That's also sine squared x. But you could also just say this is cosine squared over cosine squared, so that's 1, plus sine squared over cosine squared, which is tangent squared. So if you simplify like that, your derivative is here. Both of these are correct. Both of these are great. More often than not, this is the one that's going to be more useful in exercises. So the derivative of tangent is secant squared. But that's an interesting trigonometric identity. Secant squared is equal to 1 plus tan squared x. Some of you who maybe do math competition may know that. All right, so here's a little box with a variety of trigonometric function. This is the only one that you should really make an effort to memorize. None of the others need you to memorize them. But if in a quiz or a test you suddenly need the derivative of secant, you should write it as 1 over cosine, and then you just apply the quotient rule, and it'll give you the answer. Likewise, cotan is cosine over sine, so you can use the quotient rule as well. This one is the only one that's actually important. So moving on, these were the two absolute key points in this section, the product rule and the quotient rule. When I was insisting at the beginning of these notes about the importance of this section, that's what I was talking about, being a master, an absolute master in the product rule and the quotient rule. What I mean by a master is if I give you 100, you should absolutely do 99 correctly. If you do 98 correctly and miss 2, that's really too bad, and you're going to pay for it over and over again. So, if you take the derivative of the derivative, that is just called the second derivative. And how do you write that? Well, typically you write it like that, f double prime. You can also write d squared y dx squared. It's a little weird because the squared goes in different places. Mostly you need to recognize this as the second derivative, but I believe if you write a second derivative yourself, you're going to use f double prime or y double prime rather than this style of writing. F triple prime is the third derivative, and so on and so on. The general term, if we go beyond the first derivative, so beyond just the normal derivative, we just say it's higher order derivatives, second, third, fourth, and so on. Find the second derivative of these two examples. Y equals x to the 5. Well, there's no shortcut. You have to find the first derivative, which is 5x squared, 5x to the 4, and then you have to take the derivative again of that first derivative. And this gives you the second derivative, 20x cubed. Find the second derivative of f of x equals 4x times cosine x. That's a product. 4x times cosine x. So let's set u equals 4x. Let's set v equals cosine x and use the product rule. U is 4x, u prime is 4. V is cosine x, v prime is negative sine x. And that leads to f prime of x, so the first derivative, is equal to 4 times cosine x plus 4x times negative sine x. Great, we just need to do that a second time. What's the second derivative is finding the derivative of that. And in fact, the derivative of 4 cosine x is going to be easy. That's just 4 times negative sine x. So it's right here immediately. But it's a little bit more tricky with the second term, because that itself is a product. Again, it's 4x times negative sine x. So we need to use the product rule again for that part. So this time u is 4x and v is negative sine x. So I did that here. And now I can write the derivative of the second term. So we already found negative 4 sine x, plus I just put a big parenthesis for safety reasons so that I know I'm not going to make a mistake, and I do u prime v plus uv prime inside this bigger parenthesis. All in all, after you put like terms together, the answer is f double prime of x equals negative 8 sine x minus 4x cosine x. The second derivative has several interesting properties, but one that we've already kind of brushed on is regarding position. If you take the second derivative of the position, that gives you the acceleration. So the acceleration is the first derivative of the velocity, or you can say the second derivative of the position. So if a car has traveled t seconds and it's positioned at after t seconds is 2t squared, find the acceleration of the car at t equals 2. Well, we have the position, we can find the velocity by taking the derivative, and from there we can take the derivative again to find the acceleration, and we find a of t equals 4. The acceleration of the car is 4 meters per second squared. And that's always true somehow in this exercise. It's maybe a little bit of a surprise. It doesn't matter if the question had asked what is the acceleration at t equals 5 or 7 or 0.2, it would also have been 4 meters per second. So we can say that the acceleration is constant. Last exercise, several little things here, several questions in a row. It's a weight hanging from a spring, so, well, that's really not a very good drawing, but you get it. Oops. Here's the weight, and it goes down and up and down like this. And the position, S, which is in centimeters above the ground, so let's just say this is the ground, and so S is this length here. I'm just going to the middle of the weight, I guess. Its position above the ground after t seconds is S equals 5 cosine t plus 6. So yeah, I guess it would be better if this arrow just went to the bottom here. So find the velocity at t equals 1. Okay, I have the position. If I want to find the velocity, I'm first going to have to take the derivative. So the derivative of 5 cosine t is negative 5 sine t, and the derivative of plus 6 is 0. So velocity is just negative 5 sine t. And now I plug t equals 1 in, and using your calculator, rounding or truncating after 3 decimal, you find that v is negative 4.207. So, what do you think? Is the weight going up or down at this point? The answer is it's going down because the velocity is negative. Question B, what is the speed at t equals 1? The speed is the absolute value of the velocity. So the correct answer is the speed at t equals 1 is positive 4.207 centimeters per second. The only difference between A and B is the sign. The speed is positive. Question C, what's the acceleration at t equals 1? Answer, the acceleration is the derivative of the velocity, so I'm going to look at what the velocity is and take the derivative. And I get A of t equals negative 5 cosine t. Then I plug 1 in, and here's the answer. A of 1 equals negative 2.702 centimeters per second squared. Question D is what I asked earlier. Is it moving up or down? We answered that it's moving down because the velocity is negative. And question E, that's a complicated question that we will spend a lot more time later on. Is the speed increasing or decreasing at t equals 1? And the answer is the speed is increasing. So we will talk a lot more about that later in the year. But strangely, to understand whether the speed is increasing or decreasing, you have to look at the sign of the velocity and the sign of the acceleration and look if they are agreeing or disagreeing. So here the velocity is negative and the acceleration is negative as well. So they are kind of working together. They are collaborating at making the object move faster. The velocity is negative, which means it's going left or it's going down. And then the acceleration is pushing even more in that direction. So the acceleration is also going left, or in our example here, going down. So these two are contributing to making the object go faster and faster at that point. So that's it for this section. Thank you very much for listening.